So, well, the objective of this lesson is to understand the basic concept of eigenvalues and eigenvector. Now, before I go ahead on the concept, I just wanted to clarify what is the geometrical significance and what is the definition of eigenvalue and eigenvector. Now, if I consider a matrix, let's say 3, 0, 1, and 2, and if I multiply it with, let's say, any other vector, which is, let's say, 2 and 4, so if we multiply these two vectors, so what we get, I mean, this is the matrix here, and this is the vector. So if I multiply this, I get 3 times 2, which is 6, and 0 times 4, which is 0. And 1 times 2 is 2, and 2 times 4 is 8. So what we get actually is we get 6 and 10. Now, in a context, the definition of uh, the eigenvalue and eigenvector is that if I got a matrix, if I multiply it with a particular vector, now if, for example, 3, 0, 1, 2, if I take a vector 1 and 1, and if I multiply with this, what I get is it is 3 times 0, 3 times 1 is 3, and 0 times 1 is 0. And 1 times 1 is 1, and 2 times 1 is 2. So the answer is 3 and 3. So what you notice is actually the vector that I multiplied in the beginning and the answer that I'm getting is their exact multiple. So if that scenario happened when you're multiplying a with a particular vector x and you get a scalar multiple of the same vector, so this is referred as an eigenvalue, and this vector that you multiplied is referred as eigenvector. So when you look at this as on a diagram, actually what's happening is if I look at this context, when I multiplied with 3, 0, and 1 and 2, what is happening is that this is actually is the new vector that you got is actually just getting stretched along with this. So it is like this. So the course or the direction of the vector is not actually changing. It's not going somewhere like here. It's actually along this. So as long as it is just a multiple of the same original vector like here, or can be just here, it is referred as the eigenvalue. The value of this multiple that I get is eigenvalue, and this what I get is called as eigenvector. So let's just take an example of for how do you find out eigenvalue and eigenvector. So as per the definition, what we got is that if you have a matrix A and if you're multiplying with the vector x, and if your answer comes as a scalar multiple of that same vector, lambda is referred as this is called lambda. It is referred as eigenvalues, and this x that you multiplied with is referred as vector. Now the standard procedure is to actually, if I bring let's say ax equals to lambda x, so if I bring them one side, so what we get is if I take x common, so what I can write down is a minus let's say lambda times x equals to 0. Now obviously this I can't take as lambda, so I take along with that. I can take it as identity matrix I. Now, if x is a non-zero vector, so this must be 0. So so we talk about this as determinant of a minus lambda I, or you can even take lambda I minus a. This determinant must be 0. And when you solve this, when you solve for this, what you get is basically the characteristic equation and the eigenvalue. So let's take a proper example for this. Now assume that we are asked to calculate the eigenvalue and eigenvector for this. So what I'm going to do is I'm going to take the matrix A, so lambda I minus matrix A. The determinant of this should be 0. So I get is lambda times 1, 0, 0, 1 minus A is 0 minus 3 minus 4 and minus 1. So what we get at the end is lambda, and lambda minus 3 is basically here. This is 0 minus 3, so it is negative 3, and minus and minus become plus, so it is 3, and 4, and plus lambda plus 1. So now this we're going to find the determinant and equate to 0. So what we get is if you solve, so to find determinant, you multiply this minus this and this minus this. So your answer comes to this quadratic. And now this is also referred as a characteristic polynomial or characteristic equation. You're just going to equate this to 0 in order to get the exact value for lambda. Now, this is the most interesting part here, because now you got the eigenvector, I mean eigenvalue. Now to get the vector, what we got to do is we got to just follow the procedure further. So now when you're finding out the eigenvectors, so let's say after you get the eigenvalues here, what we got to do is we got to substitute these in our equation. So let's say these values, I'm going to substitute one by one in my equation. So let's say here we go. So when I substitute in the equation, actually, so my equation was the lambda times I minus a times x equals to 0. Now, if I take the vector x as 2 by the 2 rows and 1 column vector, so 2 by 1 vector, which is a and b, and if I multiply the matrix A, let's say here, in considering the lambda equals to 1, and this is the value that we get here. If I take lambda as 1, so what we get is the answer is 0, 0. So if you multiply out, so you get like A minus 3B equals to 0. So now from here onwards, what you take is, let's take B as T or something. So you get A equals to 3T. So if my vector is actually 3 and 1 times T, so T can be like in general, like anything. You could take T as 2, T as 3, T as 4. So what I get is the vector actually is 3, 1 here. So 3, 1 is my eigenvector for the lambda equals to 1, for the value lambda equals to 1. Now when I take lambda equals to minus 3 and you plug in this here, so for example, I would just show it to you. So when I plug lambda equals to 3, so what we get is minus 3. What we get is this part is actually -3, -3, and -1, and -3 plus 2 is 1. So this is my coefficient matrix that I get, and of course that is same as this here, and we follow the same procedure. Okay, so follow the same procedure, and you multiply out with A and B, and that answer should be 0, 0. So what we get is eventually, if I open up the bracket, I get negative A, negative B, and that's your answer here. That comes out to be, if I take B as T, let's say for example, I get A is negative T. So what I get is actually, if I take the vector in form of -1 and 1 times T. So this actually is referred as the eigenvector. Now, if you look at the context here, if I take my vector as a 3 and 1, if I take 3 and 1 like here, and if I multiply that with this matrix, you'll always get as a scalar multiple. Or anything, if you take 6 and 2, you'll get in the same direction as a scalar multiple. So this is how you find out the eigenvalues and eigenvector for a given matrix.